Welcome back, ChemStars. It's time for our last gas laws video on the ideal gas video. You know what else is ideal? Corgis. We're the ideal pet. Remember, dogs rule. Cats drool. Do your homework. Yes, do your homework. Especially, remember, always show the original equation as well as all of your units and you will do great. Remember, no cats. Ollie. Bye, guys. See you next time. Bye. Okay, so let's go over our last gas law, the ideal gas law. This is a snapshot of a gas in a container at one point in time. So the ideal gas law from your notes is pressure times volume is equal to N, the number of moles, times R, a constant, and T, temperature in Kelvin. So make sure we understand what each of those units are. And then the R value, those are a constant. There's a lot of different published values that you can use for this. So either convert everything to liter, atmospheres, moles, and Kelvin and use this number, or you can check the table. The table that you can check is at the very beginning of our gas law notes. So if you look at all these, if, for example, you want liters, atmosphere, mole, Kelvin, use that 0.08 number. But if you have liters in kilopascals, you can use this number. Or if you have liters in torr or millimeters of mercury, you can use this number. If you're in the American system, there are some feet per psi, pounds per square inch. So just always go back to this, or else just convert to the correct units that you already have. Okay. Oh, Pickles is walking around. He's going to help. Okay. So let's look at problem number 1. Oh, Pickles is crying. He's so sad because some of you aren't doing your homework. It's okay, Pickles. How many moles of radon will occupy a volume? Okay, so we've got a volume of 12.7 liters, pressure of 0.95 atmospheres, and a temperature of 45 degrees Celsius. First thing, whenever you see a temperature, we're adding 273.15 to convert it into Kelvin. So remember, we add, well, I don't know why it won't let me add. We add 273.15 to convert to Kelvin. Okay. Just like we always do, we write the equation. So our ideal gas law equation, PV equals nRT. And then let's just substitute what we know. So what is the pressure from the problem? The pressure from the problem is 0.95 atmospheres. The volume is 12.7 liters. And N, my number of moles. Remember, we use N for number of moles in chapter 12, molarity as well. Times R. Now we want to make sure we have the right R value. The one printed on the page, it is for liters, which we have, atmospheres, which we have. We're solving for moles and Kelvin temperature. So we can just take that 0.0821 number. Now this unit looks weird. It's liters times atmospheres, moles times Kelvin. In the numerator and denominator, we'll explain that more in a second. And then temperature, we already figured out. Okay, so we have to isolate and solve for N. We want to get N by itself. So we're going to isolate and solve. And when we do that, we're going to have 0.95 atmospheres times 12.7 liters over R over temperature. Now let's look at why this R value has those weird units. If we have atmospheres on top and we have atmospheres on the bottom, it cancels. If we have liters on top and we've got liters right there, it cancels. Then over here, we've got Kelvin in the numerator of the denominator and then Kelvin in the denominator of the denominator. Those cancel. We're left with 1 over a mole. If you think back to all of our algebra tricks, that's the same thing as 1 over 4. And take out your cell phone, take out your calculator, type 1 divided by 1/4. What do you actually get? You get 4. So what's 1 over a mole? That's actually a mole. So when you're dividing by a fraction, you flip and make it up into the numerator. So that means, yeah, we are going to get moles, which is exactly what we wanted. So when we plug it into our calculator, we're going to get 0.461904 moles. That's a very precise number, but we cannot be more precise than the inputs to our problem. 1, 2, 3 sig figs, 1, 2 sig figs, and then, well, technically there's going to be 3 sig figs in that temperature. So least whole number, we need to round this to 2 sig figs. So placeholder, 1, 2, look to the right. Will the 1 round up the 6? Nope. My final answer is 0.46 moles of radon gas. And there you've just done your first ideal gas law problem. Let's take number 2. How many liters, so volume is question mark, of a krypton will there be if there is 1 mole? Now, we're going to say 1.00 just so we can be pretty precise with our final answer. So change that to 1.00 moles at 101.325 kPa at 0 degrees Celsius. Okay. 0 degrees Celsius, we add 273.15. And if you look at the way I wrote this, we're actually going to round to 3 sig figs. So first step, always write the basic equation. Second step, always substitute in. Pressure, we have 101.3 kPa. Volume, we are solving for. N, my number of moles is 1. And remember, I said we're going to make it 1.00 to be more precise. Now, R, that's something we want to be careful with. We can't use that 0.08 number from the previous problem because I don't have liters in atmospheres. I have liters in kPa. So we go back to that published table, and if we have units like liters in kilopascals, we're going to use a number 8.314472. So that's where this R value came. You'll always be given a way to either find those or convert to the correct units. And then my temperature. So just do your basic algebra 1 type stuff. We want to isolate and solve for volume. We have to divide out that 101.3 kPa. So we're going to divide, isolate, and solve. And your calculator will give you a volume of 22.4 liters, which, does that number look familiar to you? What did we learn back in Chapter 9 stoichiometry? 1 mole of gas at standard temperature and standard pressure will be 22.4 liters. When we round that to 3 sig figs, well, oh boy, what do we get? 22.4. So the ideal gas law supports that use of 22.4 in our Chapter 9. We were at standard temperature, which was 0 Celsius. Standard pressure was 101.325 kPa. And we got 22.4 liters, the volume of 1 mole. Oh, isn't science fun? It makes sense. Question number 3. What is the pressure in kPa, or what pressure in kPa, so pressure is question mark, will 0.75 moles of carbon dioxide at a temperature of 25 degrees Celsius and a volume of 500 milliliters? Okay, if we look back to our R values real quick, we have liters, 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 liters. Do you see any milliliters? No. You see meters cubed. You see centimeters cubed. To keep it simple, so we don't have to do any other unit conversions, let's just convert our liters right into milliliters right into liters. So remember, quick trick is go 1, 2, 3. Volume is 0.5 liters. Start with your original equation. The pressure is unknown. It's the variable we're going to isolate and solve for. Volume is 0.5 liters. My N, my number of moles, is 0.75. The R value, when I have, well, I can pick whichever one I want, really, because whatever R value I pick, it will give me the pressure here that I need. So make sure you pick the number that goes with kPa. And temperature, we've got to convert 25 to Kelvin. So add your 273.185, you get 298.15. So we're going to isolate and solve. That means on each side, we're going to divide by that 0.5 liters. When I do that, the liters cancels. The liters cancels. The moles cancels here. Kelvin cancels here. And we're left with kPa. So that means the algebra is set up right. Really take the time to show your units canceling, because that will let you know if you've isolated and solved and set up your algebra correctly. When you do that, your calculator will tell you 3,718.4397. Too precise. 2 sig figs. Well, that's going to be actually 3 sig figs. I made that 500 point to give us an extra sig fig right there. So we're going to say 3 sig figs. 2 is my least number. So if we want to round this to just 2 sig figs, 1, 2, look to the right. The 1 doesn't round up. Final answer is 3,700 kPa. Okay, a couple more problems to go. What temperature, so T equals question mark, will 4.0, let's be precise, of 20 period liters of helium occupy at 740 millimeters of mercury? I did that so we have 2 sig figs in all of our numbers, just so we can be accurate. So ideal gas, PV equals nRT. Pressure from the problem, we plug in our 740. Volume is 20 liters. My number of moles, N, is 4. Since I'm in millimeters of mercury, that's actually the same thing as torr. So I'm going to look at this number right here, my 62.36 number. Torr and millimeters of mercury are the same unit, so I'm pulling that constant. Or you could convert that into atmospheres and use the 0.08 number if you want. And then temperature, we're trying to solve for. Okay, so we're going to isolate and solve. We would divide these out. And here's what your calculator is going to tell you. It's going to tell you 59.329 Kelvin. But do we often get any problems giving us Kelvin? No, usually the problems give you Celsius. So we're actually going to subtract our 273.15 and get a Celsius answer as well. So in Celsius, that's negative 213.8205. Last thing is round for those 2 sig figs. So 1, 2, we're going to have 59 Kelvin. 1, 2, we're going to have negative 210 degrees Celsius. Remember, it's degrees Celsius, but it's just Kelvin or kelvins. There's no degree there. Okay, and I think this is our last problem. Oh my goodness. We did it, guys. We made it through the year. So, how many grams? Now, this is different. We haven't asked you for grams before. Let me extend the page a little bit here. Oop, too much. How many grams are there in a sample of CO2 that has a volume of 4.5 milliliters, a pressure of 320 kPa, and a temperature of 45 degrees Celsius? Before we start plugging things in, let's just identify what we're aware of, what we know. Okay, they want grams. I don't have a way of getting grams from the ideal gas law equation directly, but I can solve for moles, and we've spent a bunch of time this year converting moles to grams using the molar mass from the periodic table. So that's going to be one step. The volume is 4.5 mils. To make it easy, let's put it in terms of liters, so move your decimal 1, 2, 3. Volume is 0.0045 liters. Pressure is 320 kPa, that's fine. 45 degrees Celsius, though, I need to convert that to Kelvin. So add your 273.15, and now we can start plugging things in. So pressure, 320 kPa, volume, 0.0045 liters, we converted from mils. N is unknown, we're trying to solve for it. And since we're in kPa, I'm going to use that 8.31 number. Where did I pull that from? Right here, kPa, 8.314. Remember, that's just the constant that helps everything work. And then temperature, 318.15 Kelvin. So to solve for number of moles, I need to divide these two terms out to the other side. Do the same thing to each side. You're going to get 5.44372.138 moles of CO2. Don't round your number here because this is not my final answer. Keep that in your calculator, and then we're going to convert the moles to grams. So if we have CO2, carbon's molar mass is 12.0. Oh, I wrote it wrong. Pretend that I wrote it correctly. It's not 12.10, it's 12.01 grams per mole. Plus there's 2 oxygen, and oxygen's 16. So carbon dioxide has a molar mass of 44.01 grams per mole. Get that from the periodic table, or maybe you've just memorized it by now. So all I have to do is I have to take moles times the molar mass. You can set up your factory labeling if you want, or look at my units right here. I have moles on top, moles on the bottom, grams will be on top. I get 0.0239578 grams of CO2. Again, that's too precise, so we need to round for our correct number of sig figs. 2 sig figs, 2 sig figs, temperature actually has 3 sig figs, so we want to round it to 2. Decimals present, begin counting at the first non-zero from the Pacific. So placeholder, 1, 2. Right here's my second sig fig, look to the right. Will the 9 round that 3 up? You betcha. My final answer is 0.024 grams of CO2. And that brings us to the end of our last chapter 10 and 11 homework problem. You've done a great job this quarter. I'm proud of all you. Remember, don't wait to be great. See you next time. Bye.